Hello friends, today I am going to discuss Sympy, symbolic computing. Symbolic computing is it is a different paradigm in a computing compared to numerical array based computing introduced in the already we have discussed in the previous video. So it's a software. It is a software and computer algebra system. You can say the CAS representations of mathematical object and expression are manipulated and transformed analytically. So scientific Python environment, actually the main module for the symbolic computing is a Sympy, symbolic Pythons. Sympy is entirely written in a Python and it provides a tool for wide range of analytical and symbolic problems. So let's see, first we need to import Sympy. So I have imported here Sympy and Sympy dot init underscore printing. So now it takes some time. It has been imported. So here we can see the Sympy dot init underscore printing functions which configure Sympy printing systems to display nicely formatted renditions of mathematical expression, as well as we will see like in the future, because this is the I am working on the Google platform like a Jupyter notebook, so it will be convenient. So now after that I am importing from Sympy import I, pi and o. So let's see NumPy and Sympy, as well as like many other library also we will see. It provides many functions and variables with the same name, but these symbols are rarely interchangeable. For numpy.py is a numerical approximation of a mathematical symbol pi, while a sympy.py is a symbolic representation of pi. So it is therefore important to not mix them up and use, for instance, numpy.py is a place of the sympy.py. So when doing a symbolic computations. So one more thing, the same holds like a true for the many fundamental mathematical functions. We can see such that we can take an example sine where sympy dot sine. So therefore when we are using a more than one package in computing in with the Pythons, it is important to consistently use namespace. So first, symbols symbol's name is a string. Symbol name is a string. So which optionally can contain latex like a markup, make a symbol's name, display well. IPythons reach a display system. So the name of the symbol object is set when it is created. So symbol can be created a few different ways in a Sympy using sympy.symbol, sympy.symbols and sympy.var variables. So let's see, x will equal to sympy.symbol and x and print x. So we can see here it has been printed like this. So variable x now they represent the abstract mathematical symbol of x, of which a very little information is known by a default. So x could represent, for example, like a real numbers, integers, complex number, functions, as well as a large number of other possibility. So next, just I am going to like a y will equal to Sympy dot symbol y as a real. So we can see here your y will represent like this. Y is real, and you can also ask the questions y is underscore real. You will get a true result. Similarly, Sympy dot symbol z imaginary and is dot real, because if you are asking a question, so you have gotten like a false. Sympy dot symbol like a imaginary and is underscore finite. So you can see here, and you have gotten like a this is it real and finite. So similarly we can see the real, imaginary, positive, negative. Okay, you can also write here like a is it x and is it positive x and y, it has been printed. Primes, infinite. So number of way we can see here. So let the Sympy dot sqrt square root of the x square. So we can easily print here, look like this, x root square of this. Similarly, if you want to write a cubic and others also, we can create here. So you could see here y square. So Sympy dot sqrt and y to the power this. So so look here. So this means here we have created the two symbols. One is the x, another is y, and computed the square root of the square of the symbols using the Sympy function Sympy dot sqrt. If the nothing known about the symbols in the computations, then no simplifications can be done. So if on the other hand the symbols is known to be representing a positive number, then obvious square root of y square will equal to y. So and Sympy correctly recognize this in the later example. So after that symbols you can write here n1, n2 and n3, and Sympy dot cos n1 into pi. So you can also represent like this. N cos n pi. So to formulate the non-trivial mathematical problem, and it is often necessary to define a large number of symbols using symbols to specify each symbol one by one, may become tedious and for a convenience. So Sympy contains a function Sympy dot symbol for creating a multiple symbols in one function call. So similarly we can take like a, if you want to write simpy dot cos n to pi like this, so minus 1 to the power n, and if I write here like a n3, so we can see here minus 1. After that, just you can say like the some different variables. So this is a using a like a Python's tuples unpacking syntax together with a call to the Sympy dot assembles is a convenient way to create like a symbols. This one excuse me, so it has been created like A. Now the other we can see here the numbers. The purpose of representing mathematical symbols as a Python objects is to use them in expressions trees that represent a mathematical expressions. To be able to do this, we also need to represent other mathematical objects such as numbers, functions, and constant. In this like a Sympy class for representing numbers objects, and all of these class have many methods and attributes shared with instance of symbols. So just I have taken like a I as a variable Sympy dot integer 20 and type like a I will equal to this one. After that you can ask the questions I is underscore integer and real and odd. So it true because is it integer? Yeah, it is real, and but it's not a false. Odd, so you can see here false. Similarly you can see like a, so we can cast instance of Sympy dot integers and Sympy dot float backs the Python's built in a types using like a standard types of castings like a int I and float f. So let's see the f as a the float dot 2 comma 3. So what type? So Sympy dot code number dot floats. So f dot integer, f dot is underscore real, if dot odd we could see here. Similarly if Sympy dot 19 and Sympy 2 and 3 we can see this now. If you write the I to the power like this one, so you can represent like this. Sympy dot fractionals you can write there, and another the Sympy dot rational we can write more value. So these are the basic only. The integers means we use the integer class to represent like integers, and it would pointing out that there is a difference between the symbols instance with assumptions integers will equal to like a true, and similarly we can say the integers Sympy are either arbitrary precious meanings and that they have no fixed lower and upper bounds. So which is the case when representing integers with a specific bit size. As a for example, Now if you take like a float, so we have already like encountered like a type of the Sympy. So float in the previous sections already we have seen. So float is arbitrary precisions, and in a contrast to a Python built in a float types and float types in a NumPy. This means that a float can represent a float with an arbitrary numbers of decimals. So when a float instance is created using its constructors, there are two arguments. First argument is a Python float or a string representing a floating point number, and the second argument is a precisions of the float objects. So like this the Sympy, and another is the rational. So a rational numbers is a fractions like a p upon q integers, and numerator is the p and q is the denominator. So the Sympy represents this type of the numbers using a Sympy dot a rational class. So let's see just how do I write your rational number. So according to the Sympy, just look here, it has a represent like a, if you are actually second variables has been printed. So you can, if you can multiply here, so let's see p by q, just I am going to the multiply here. So you can see here, look like it's in this fractions like a 12 will multiply like this, and but if you write like a p and over q like this, so you could see look like this p over q like a 12 upon 12. Okay, so you can represent this way, automatically it take. So I think it's clear. So we can also multiply and can also like a do this. Now next, like something constant and the special symbols like a Sympy dot pi and Sympy dot e, the base of the natural logarithm. E will equal to expressions like 1, and y like a Euler gamma, Sympy dot Euler gamma, like a Euler constant. Sympy dot I is the imaginary unit, and Sympy dot double O means like a infinity. And we can also use like a functions. So Sympy dot functions like a symbol functions, and we can easily create like these functions. So let's see, just you can create this like right here, and if I am going to discuss like a function, and I write here x comma y comma z will equal to Sympy dot symbols dot Sympy dot, one is the symbol, another is symbols. So we need to the symbols because I am creating the more than one, taking a one value. So look like x comma y comma z. After that, just I write here f will equal to like another variable Sympy dot function dot functions and f and type f. So first, so we can see here first, let's see, and I'm going to write here type f. Yeah, so you can see the functions, undefined functions. So you can see similarly fx, if you want to print here like f and x, like, so you could see here like a fx. Similarly, if you write the another functions, if you write like a g will equal to Sympy dot functions dot Sympy dot functions, and you write here like a g inside of this quotation like a g, and g is the another functions. Then write x comma y comma z, x comma y comma z, and I want to print like a g. So could you see how it has been printed like this? These functions has been created. So it's very clear, but just if you want to like a g as a x, y and z, it has been created. But if you write like this, g dot free underscore symbol, yeah, it has been symbols. So what happened? G dot free underscore symbols we could see here inside of the curly brackets. So here we have also used the property free underscore symbols, which returns a set of unique symbol contains in a given expression. Yeah, in case to apply the undefined functions g to demonstrate that an applied functions indeed is associated with a specific set of input symbols. This will be important later in this, so you can understand. Now after that, because most of the time we will see in the derivatives, we will consider when we consider derivatives of the abstract functions, and this will be the important. But let's see in the calculus. So calculus, just we are going to define like a Sympy dot functions. So we can easily write here the functions. So let's see, just I am going to write here the functions. So how do we see? We have already discussed fx. But if I want to write here like some trigonometric functions. So like a Sympy dot sin x, is it possible to the write here? I think so. Just I am going to write here. I have create like a diff. So this is the differences of differentiate fx, like we can see here, and another, if I am writing this means like a Sympy dot sin x, P dot sin x. This is the trigonometric functions. So yes, we can look like this. Now dif means differentiate. So diff, and because I have differentiating the twice, so we can write this one. Otherwise, just if you write here only once, so like here, this is the first time derivative. Similarly, what happened? Is it possible to write the thrice? So let's try here. So could you try here like this? Yeah, it has been like this. So 3-4 times you can easily write this functions. So these expressions we can easily represent, and if I want to write the something like this as expressions, one more thing, just let's try here. Okay, like some functions look like 100 times you can write here, you put here the 100. And one more thing, just if you have the Sympy dot functions and gxy, and now I am going to the differentiate here, so we can also write like this way, double derivatives. And after that we can also write this way, like x as a 3 and y as a 2, so total difference is the 5 and x, so we could see here like this. If you want to write here x like 4 times and y is 2 times, so we can also like this. Another expressions we can represent like suppose expr and x to the power x means 4, x to the power 4 plus x to the power 3 and x square and x1. So you can see here expr, it has been print like a 4x cube 3x square plus 2x plus 1. And if I can write m expressions, so let's see, could you share? So you can see here like, so I hope you can understand. So it has been differentiated, so this is the differential part, not other equations. So expr is the equation and this is the differential parts. So similarly the expr like x with respect to the x and x means it is a differentiating twice. So let's see, whenever if you differentiate like a 4 times 3 is 12, so 12 if you multiply like here 3 times 2 is the 6, so it becomes a 6 and it becomes like a, again you can see here like a x, so it becomes 1. Okay, only 2. So I think it's clear. So whole differential parts we can easily write the any expressions as the differentiations with the respect to the, we can easily differentiate with the Sympy. Now let's try the another is the Sympy and dot sine x y, and now the Sympy dot cos x by 2. So how do I write the complex equations, and we can also direct could you differentiate and not. So is it possible to the differentiate? Let's try here. Yes, it's possible to the differentiate here. Yeah, you can write here like a, what is your equation. So let's try here. So first I am going to write this equation, so it will be the better to understand, like this is the equation and I can expr, so expr, so this is your equations and this will be the your differential equations. This is your equation like sine xy and cos x by 2, and now I am going to the differentiate here. We have gotten the exactly within seconds. Now similarly d will equal to, I have written here the Sympy dot derivatives and Sympy dot express and Sympy dot the cos x and this one. So we can see like this, and if you want to the like this derivative will be, you could see here. So I hope manipulating like expressions, this is a way to we can easily express. So we can Sympy dot simplify, Sympy dot tricks IMP, like simplify expressions using a trigonometric identity, and also simply an expression using like the law of powers, and Sympy dot comps IMP, like simply the combinatorial expressions, Sympy dot rats SIMP, writing the common denominators. And another just expansions also we could try here. So let's see, just you have written here, and another just if you want to do it, so it can do it easily. So the number of the expressions we can also write like this. If I write here like a expr will equal to, okay, just I write here x plus 1, and it will multiply with the like x plus 2. So need to write here x plus 2, and now I want to get here output expr. So you can easily get here that expr has been like this is your output. So this will like but if you write here like if you apply here like Sympy SYMPY and dot expand Sympy dot expand and expr then we can see here this is your equation. So this is a way we can easily get here. So I hope you can easily understand. Similarly, just factor, collects and combines. So we can also write a factor like this. Suppose I need to get here factor, so the Sympy dot factor like this. Could I write here double x square and minus 1. Let's see how. So just I am going to the factor like once away, so it's possible to get here the factor because I have already used the function. Right, so I have gotten here the factor, right? So we can also write here the 60. Let's see, just gotten here the factor. Similarly, just if I write here like 4, 8, it's possible to get here factors. Yeah, absolutely you are right. So we can get a factor. Okay, so it's a very simple, and just if you write here 7, could I get a factor? It's, so it's, we can write as it is. So it's a good way to, we can apply here how to get your factor, and it's possible to you can get factor, not possible to you can get here. So I think now you are very comfortable, we can use Sympy, and another like a part like a together, and we can also like a cancel. So you can apply the sum value like if you write here, let's try Sympy dot apart and 1 divided by x and 2, now plus 3 to the power x plus 2 and then x comma x 1 divided by, so I think we need to the write here inside of this bracket here, and another we need to put here the another bracket. So let's see how do I write. So yeah, we can write easily in the fractions. Similarly, a part, so apart, together and cancel. So the this is the mathematical simplification that we will consider here is a rewriting the of a fractions, and the fractions Sympy dot apart and Sympy dot together, which respectively rewrite these functions. And next, just we can also like additions, subtractions and multiplications. So this is a way we can easily. One more thing, just we want to like evaluate some numerical evaluation, so we can also evaluate like Sympy dot like a numerical, so we need to add capital N and like a 1 plus pi, sorry for that, like a pi. So what is this value? Just 1 plus and pi, so we have cut it here like this. So pi and 50 we can also write here comma and 50. So we can easily like when working with the symbolic mathematical, so it is almost invariable sooner and later required to evaluate the symbolic expressions numerically. So I hope this concept is clear. So after that, just it's functions, how do I write the derivations and how to express the any. Next, the integrals. So integrations means like in Sympy, integrals are evaluated using the function Sympy dot integrate, and formal integrals it can be represented like using a Sympy dot integral. So like which is, in this case with a Sympy dot derivatives can be explicitly evaluated by calling the dotted methods. So integrals comes in two forms, definite and indefinite. So where a definite integral has specified integration limits and can be interpreted as an area or volume, while an indefinite integral doesn't have integration limit and denotes the antiderivatives, like an inverse of a derivative of a function. So simply handle both indefinite and definite integrals using the simply dot integrate function. So if the simply dot integrate functions is called with the only an expressions as argument, the indefinite integrals is computed. And other hand, the a definite integrals is computed if the simply dot integrate functions additionally is passed a triple in the form like a parenthesis x comma a comma b, and where x is an integration variable and a and b are the integration's limits. So for a single variable function fx, the indefinite and definite integrals. So let's see some example here. Just I am taking a, b, x, y will equal to simply dot symbols like this one, and f will equal to simply dot functions fx and simply. So let's see what happened. So just I have seen the integral sign fx, this functions has been with respect to the dx. Simply integral, and if I write here the simply dot integrate, and like a function's range has been given, so from a to b, and it's a very beautiful way we can easily represent like this. Now the simply dot integrate, simply dot the sin x, so it has been like a integrated of this sin x, and I have gotten the output here like a minus cos x. This is the integration of sin x. Now the simply dot integrate the simply dot expressions minus x square, and another is the x 0 and infinity. So first we need to write here these expressions as it is. So it's a like a definite integral can also include a limits that extend from a negative infinity and or a positive infinity using like a simply. And expressions just we can write here x plus y whole square and integrate here. So we have gotten a direct output. So the computing integral symbolics is in a general like it is a difficult problem. So and so the simply will not be able to give some symbolic results for the any integral. So you can come up with, so when the simply fail to evaluate the integral, an instance of the simply dot integral, so represented like a formal integrals is returned. So similarly, just if I am going to like sometime you can also write a multivariate expressions. So just if I write here like ex pure and will equal to simply dot sign and x times simply dot ex t and y, and just first I need to write here this expression. So exp I have written and just you can see here what is your expressions like this. Now I want to integrate these expressions with respect to the x. So let's see here. So just I am going to write here like e Sympy y m p y dot integrate dot t integrate, yeah, dot integrate and expr with respect to the x. So you write here, I can write here expr. This is the expressions with respect to the x. So let's see it's possible and not possible. So yeah, within a second we have gotten just output minus e to the power minus y and cos x e to the power y. It's very very. So the same expressions we can also write, and we can create a number of v. Next we can also apply like in series, and this is what is the series expansions are and the important tool. Okay, what is this? Okay, so tool in the many disciplines in a computing, and with a series expansion and arbitrary functions can be written as a polynomial with coefficient given by the derivative of the function at the point around which the series expansion is made. So by truncating the series expansions at the sum order like a n, yeah, you can say also like a nth order approximations of a functions is obtained. So in Sympy, the series expressions of the function or expressions can be computed using a functions like a Sympy.series. Yeah, otherwise you can series methods as also available in the Sympy expressions. Sympy.series is a functions and expressions that is to be expanded. So let's see some example like this. Just I have written x and y, Sympy and symbols x and y. F like a Sympy functions fx, so and Sympy dot series like fx. So it has been written like this. Could you see in front of you? Yeah, so we could see here. So it's good to write here, and if you want to write it as some complex here, so Sympy dot a symbol and in the series, so it's possible it has been written like this. So next stage, so to change the point around which the functions is expanded, we specify the x0 argument as in this example. So and another, just if you want to remove something like the, here we also specify n will equal to 2 to request the series expansions with only the term of 2 and include the second order. Note that the error due to the tourniquets terms like are represented by the order object O, and the order object is useful for keeping track of the order of an expansion when computing with a series expansion, such like a multiplying or adding a different expansions. So you could see like this one. So you have given another, sometime we will get this problem, just I am not discussing this one. So but after that, let's see just I have taken in the series like a trigonometric functions Sympy.cos x series, so it has been expanded like this. Sin x series, it is automatically expand like this. Tan x, you can also do this one. So the Sympy expansions exponential series also we can see here. So it's a very well and beautiful, you can easily expand series also. So I hope it will be helpful. So let's see the discuss the some limits. So the limits is the another important tools for the calculate is the limit. So like which is a denote the value of a functions as one of a dependent variable approach as a specific value as the value of the variable approach negative or positive infinity. So an example of a limits is the one of the definitions of the derivatives. So let's see, just if you want to like a Sympy dot the sin x by x, this is the basic formula and its value I have already gotten. Similarly the limits with we can write the Sympy dot cos and h between h and 0, so we can write this. One more thing, just the summations we can also like a sum, so it's possible we can write there. So these are the basic way we can easily represent. Next time I will discuss like some different sum and product we can also write. So I will try to discuss like a linear algebra, and I hope this will be helpful for someone. So thank you very much.